right, let's take a look at the Objective 5 from Practice Test C, the applications of the ideal gas law. This entire series of questions either will ask us to solve for density of a gas at non-standard conditions or to solve for the molar mass of a gas at non-standard conditions. So applications of PV equal nRT. Let's just go back and look at our formula page. If there are applications of PV equal nRT, and you know what? The last series of examples reminded us that moles, N, is really nothing more than grams, the mass measured in grams, or the formula weight called molar mass, RT. One of the derivations is to solve for molar mass. So in essence, what if the X that we're trying to solve for is the molar mass? How might we pull that out? So, I mean, this really is the same equation, just where the X is the target variable. What might that look like if we're trying to solve for the molar mass? Well, ultimately, P times V times molar mass is equal to G times R times T. Just rearranging that by multiplying this, it comes up there. We'll divide both sides by P and V, and this is on your test-taking page, or it should be. Double check. The mass measured in grams times the R constant times the Kelvin temperature over the product of P times V. This indeed will get us the molar mass. Make yourself a note. This comes out in a unit of gram per mole. A second application of the PUV equals nRT equation is trying to solve for density. Keep in mind, N, as we were well aware, is mole number, grams per molar mass, over R times T. What would the equation turn into if we're trying to solve for gram per liter, which is the very definition of density, gram over volume unit? Now, how does that derive? Well, let's bring that molar mass unit up. P times V times molar mass is equal to G times R times T, grams times R constant times T. We want to bring over the RT to this side, so they're gone. And I want to divide by the volume, so it comes to this side. See the density? There it is. Volumes then simplify. So what have we ended up? Gram per liter. We'll take the pressure times the molar mass of our gas over the product of the R constant and Kelvin temperature. It's a times. R times T is a product. P times molar mass divided by the product of RT, and we get a density for our gas at non-standard conditions, and that density will come out in a gram per liter unit. So these are indeed the two equations that end up to be just simply put in the numbers, churn out the answer, but you can now just review how they have been derived. Make sure these two formulas are indeed on your formula page. Let's do a read-through. Problem 1. Calculate the density of diphosphorus pentoxide at 748 torr and 158 degrees Celsius. Torr is an mmHg, millimeter of mercury, on our barometer. Let's go to work. Problem number 1. Again, Practice Test C, Objective 5. Here we have, oops, let me get there on my paper, sorry. Calculate the density. Alrighty, so density, D, in grams per liter, just so we remember the unit there. Gram per liter is a density, a unit. Recall what we need? P times molar mass over R times T. Why don't we get our parentheses ready? Pressure times the molar mass over the product, remember, of R times T. Alrighty, so here we go. Density of diphosphorus pentaoxide. Alrighty, so here we have pressure, 748 torr. 158 Kelvin units. So, all right, 158 into Kelvin units. 11, here are my 1, 6, and 7 is 13, 3, 4, 431 Kelvin. R has to match the pressure unit, 62.4. See, I'm just making it a product, R times T. We have our pressure unit. What I have to do, a little simple calculation, I got to find the formula weight of P2O5. Phosphorus weighs 31, but there's 2 of them. Oxygen weighs 16, but there's 5 of them. Let's sum the formula weight of P2O5. So 31 times 2 added to 16 times 5. The molar mass is 142 grams. P2O5 added together. So let's hit 748 times 142 divided by the product, so make sure you're using a parenthesis, 62.4 times 431 Kelvin units, close parenthesis. Density of this gas at these conditions, 3.949. So let's do 3.95 G over L for diphosphorus pentaoxide. Number, unit, label. A+ answer. Onward we go. Calculating a molar mass. Here's a density. -40 is the temperature. 745 torr units for pressure. Well, let's see. We want to target the molar mass. So here's my formula, just off your formula page. GRT over P times V, Gert over PUV. Let's find that molar mass. Molar mass is grams times R times T over the product of P and V. Here's what we're given. Calculate the molar mass. So there's my target. It's a density of 12.135 gram per liter. You know what? That just actually gave us two values. There is exactly 12.135 grams in every 1 liter. That's what this means, isn't it? How many grams for every 1 liter? So it's given me a V and it's given me a G, gram per liter. There is 12.135 grams. There's my G. Here's my R, there's my T, over the product of P times V. Well, the V is 1 liter, gram per liter. Temperature was -40. So that's 233 Kelvin units. Right, where does that go? Temperature. See it up here? Temperature. So we'll put it right here in this parenthesis. 431 Kelvin units. Oh, wrong number, 233. Good thing I can erase. 233 Kelvin units. What was the pressure unit? 745 torr. So here's the R of 62.5. GRT over the product of P times V, where the density provided us with two values, the grams in every 1 liter. Now hit with me, make sure I don't make a calculator mistake. I'm good at those. 12.135 times 62.5. Isn't that 62.4? Oh, Linda, that's a moment I can fix before I put my final answer there. 12.135 times 62.4 times 233 Kelvin units. And then I'm going to divide, parenthesis, 745 times 1. And what do we find? 226.66, I'll do 0.7 gram per mole, the molar mass of our gas. Can't label it, it wasn't given to us in terms of identity. GRT times P over V gives us the molar mass of our gas, 226.7 grams in every 1 mole of the gas. Number 3. We're going to calculate the molar mass of a volatile. It just means it evaporates readily in the Dumas bulb method. We did this lab. Here's our mass, 5.723 grams. Volume of the bulb, 1750 cubic centimeters, same as a milliliter. Cubic centimeters, same as a milli. 789 torr, temperature's 90 Celsius. Let's find the molar mass of our unknown gas. Go to work with our formula. Molar, oops, that's a lot of M there. Molar mass of our gas. G times R times T over the product of P and V. Let's plug it in. The mass was 5.723 grams. There's the G. The R constant, the T in Kelvin over the product of P and V. So let's keep reading. Volume 1750 cubic centimeters, cc or cubic centimeters, is the same as a mil, so I need to put that in actually as 1.75 liters. Alrighty, so change that cubic centimeter. In my head, it's same as a milliliter, and then divide by 1,000. And that's the volume unit, isn't it? And that volume unit goes down here in this spot, 1.75 liters. 789 torr, so there's my P. As soon as I wrote torr, I also know the gas constant, R, has to match. Temperature of 90, 363 Kelvin units. We have our mass times the constant times the Kelvin temperature, divide by the product of P and V. Let's hit that. 5.723. Divided by, multiply by 62.4, multiply by 363, divided by the constant, or the product of 789 times 1.75. So that's in a parenthesis on your screen, equal. And here we have the molar mass. I'm finding on my screen 93.885, shall we say, how about 0.89 grams in every 1 mole? Good work. What's next? Going to calculate the density of sulfur hexafluoride given pressure and temperature. Given pressure and temperature, calculate a density. Test taking tool page. Density. P times molar mass over the product of R and T. P times molar mass over the product of R and T. Plug the numbers in as we read them. Calculate the density. So density is equal to, here's my pressure, here's my molar mass. This is going to be the product of R times T. We have sulfur hexafluoride. Hexafluoride is 6 fluorine. Sulfur weighs 32. Fluorine is 19, but there's 6 of them. So here I have 19 times 6 plus 32. How about a molar mass of 146? I'll double check my math. 19. Yeah, I got the same thing twice. So molar mass there, 146 grams sulfur hexafluoride. It says we have 50 grams. Oh, that's problem 5. 1.431 atmospheres. So that's this guy. There's the pressure, which gives me the R constant to match is 0821. And 40 Celsius, 311, 313 Kelvin. Plug them in, churn out the density. 1.431 times 146 divided by the product. So use your parentheses, 0.0821 times 313. Density I'm finding is 8.13, so let's say round a little bit, grams per liter of sulfur hexafluoride. Almost there, and one more. Number 5. Whoops, too far. Calculate the molar mass. 50 grams, occupied a volume of 1,500 mils. There's my pressure, there's my temperature. Pretty much plug them into the formula. Molar mass is found by taking grams times constant R times the Kelvin temperature over our product of P and V. We have that on our formula page. We derived it right at the start of the lesson. Gert over Puv. Plug them in. 50 grams. Let's just get our parentheses ready. Product of P times V. 50 grams goes in the G spot there. The 50 grams, we have 1,500 mLs, so that's 1.5 liters for the V. We have 100 kPas. That gives me the R of 8.31 and 45. Ooh, I almost wrote that in there, silly me. 811, 318 Kelvin units. G is 50 grams in that spot. 8.31 is in the R. 318 Kelvin units for T. P, 100 kPa. Volume have been converted to a liter. It must be in a liter when we use the ideal gas law. So what do we get? 50 times 8.31 times 318 divided by the product. So use your parentheses. 100 times 1.5 inside of a parenthesis. How about, ooh, big one. Let's see, 880.86 grams per mole. You did it, my friends. A plus on your last objective for the round 1 testing here. You're ready to try again.